Hey, welcome back. Here we are. We're basically at the end of fields. And so we've done electric fields, magnetic fields, and now here's the final thing where we're going to, final little component that we're going to be talking about with magnetic fields. And so generally, here's where we're going. Generally, what we've seen is if we've got a magnetic field, B, right, and a current in a wire, we've always seen that they've been perpendicular, okay, 90 degrees, so that's what you'll see in your notes. But what if the wire is running at an angle to the field, okay, so it's an angle, it's not right on the field, then what happens, okay, and so this is different. When it's perpendicular, we don't have to worry about it. We're used to our formula, which is F Bill, right? Don't know who Bill is, but, you know, we're used to it being perpendicular, but what if it's not? And so here's where we get to this. We got to work with components, okay? And so our big idea, our big concept is this idea. If a wire was running parallel, right? If there's current going parallel to this field, okay, so this is a wire with current in it, it would feel a force of 0, okay? That's the big idea. If you're in a magnetic field and the wire is parallel to the magnetic field, there's no induced current, okay? So that's the big idea. And so if we break this into components, we would get two pieces, okay? So I'll use blue for this. We would get this piece, okay, and this would be the excuse me, this is the current times, since this is the current, this is adjacent hypotenuse, this would be times cos 25, and this side would be sine 25, right? I times sine 25. And now this component would be 0. It would induce 0 force because it's parallel, and this would be our regular. This is what we should plug into F Bill, right? And so we need a simpler way to do this. And so what we're going to do is we've got this formula, and this is the formula we're going to use, okay? The formula is FB equals B I L. Looks good so far. We've done this before. And then we're going to do sine theta. And what theta is, so we're very familiar with this formula, but what theta is, and this is what's super important, theta is, I should have used that, the angle between I and B. Okay, now this is important, and it's so easy to get mixed up with this. That is between the current and the magnetic field. You should know that hopefully by now. Alright, and so what this means is we're going to use the sine piece. And so the reason I gave this example, because I want to do this all at once, is in this case, the sine piece is the piece we don't want. So I don't know if you're following, it's tricky to follow, but the rule is if it is parallel, if the current is parallel, okay, so like this is parallel to this, right, then there is no force induced. And the sine piece is how we got it, except for this angle. So let's look at this angle 25. This angle is between the current and some imaginary line that we drew to the east. Do you see that? Like, where did this dotted line come from? It's imaginary. Okay? And so if we would set this up differently, okay, what's the angle between the current, okay, and the magnetic field? Oh, well, the magnetic field is north. The current is here. This is the angle between the two. Okay? And what is that angle? Well, this whole thing is 90, and so this is 90 minus 25, so that's a total of 65 degrees. So that's little triangle math. Hopefully we're okay with that. 65 degrees. This is the angle that we should need to use, not should, need to use, and then our formula is all good. Okay? And so if we use 65, then we'll see very quickly that the up component, the parallel component to the 65, this would be I cos 65. That's the part that just is 0. And then we would get this as well, component. If we did components, then we would get I times sine 65, and that would be the perpendicular to the magnetic field component of the current. So there's a lot going on there. But essentially, as long as we're using the angle between the two real things, between the current and the magnetic field, then we can use this formula. And so let's do some examples. A 10 amp north current. So always draw it out from now on. Whenever you notice that we've got current, okay, that's I equals 10 amps north. Okay, we've also got a length, that's our L, 2 meters, and we've got a magnetic field, okay, that's B, and then we've got an angle with it. Then always, let's just draw it out to make sure that we are using the right components, okay? So we just draw it out. And so we've got to be familiar with these things. And the nice thing is we don't actually have to. So I've always said if you've got an angle, right away break it into components like we've got here. We've got an angle components. Because we have this formula, we don't need the components, okay? We just need to make sure we've got the right angle. So this angle is super important. So let's draw it out. We've got I is north. So I'll try to do it like this. I is, I is north. Okay, now we've got a magnetic field that is 30 degrees north of west. Okay, that means if we started off going west, okay, we're 30 degrees north of that. So this is 30 degrees. All right. So hopefully you can see right away, we drew this 30 degrees off of an imaginary line. And that's not what we want. So which angle do we want? We need this angle, which must be not 30 but 60 degrees. This is the one that we want. Okay? And then we're done. And so the rest we can just give her, right? So we're looking for the force, and so what we'll do is use our formula. BIL and sine theta, and we can use this formula as long as we are using the correct angle. And in this case, that's the 60 degrees. And so we've got 6.00 times 10.0 times 2.00, and then we do sine 60.0. Now we punch that into our calculator, and we get 104 newtons. Okay, awesome. All right, and so this isn't the typical we would expect 120, except for some of it was parallel to the magnetic field, so it was useless. And so we get 104. Wait a minute, we need a direction. Okay, use your right hand rule. Use your right hand rule. We've practiced this. Okay, and we've got to use the component that is perpendicular. And so once again, red is for your fingers, blue is for your thumb, and you should get your palm is now facing out of the page. So make sure you can get that. We've practiced that a bunch. Hopefully we're good on that now. Okay, a 3 meter long wire. So let's just get going again. Length is 3 meters. I'm going to skip sig figs for speed. Now we've got a magnetic field of 4.56 Teslas east. And we've got a current of 2.15 amps. Oh, I used a different form. This is essentially starting at east, going 25 degrees north. So this is north of east. 25 degrees north of east, just so we're clear. This means starting at east, going 25 degrees towards the north, so north of east. So this is 25.0 northeast. Okay, so once again, let's draw this out. We've got our current is north of east, which means if we start going east, we are 25 degrees north of it, like that. Okay, and that's our current. And now if we do our magnetic field, it is east. our 25 is the one we want. It is between the magnetic field and the current, and so it's perfect. And so let's use that. And so then it's pretty simple, straightforward. Now we just plug and play. We've got FB equals, this BIL sine theta, and so we've got 4.56 times I, which is 2.15, times L, which is 3, times sine, and we are using the 25, and we get our answer of FB equals 12.4 newtons. And the direction, again, we still need a direction. Force is a vector. I don't know if I added that up here, but it is in fact a vector, so that's why we're getting direction even when we don't want to. Force is a vector, and so once again, fingers in line with the magnetic field, so fingers are pointing this way, and thumb, which component is perpendicular? Even though it's not much of it, this is our thumb. Okay, and so if we do that, fingers and thumb up, we can see very quickly that our force is directed into the page this time. Okay, and so that is our final answer. So this is pretty cool stuff. We can predict, like, it's not always going to be 100% of the energy is creating a magnetic field. Is creating a force. It's only what is perpendicular, so we can figure that out using this formula. Okay, great. So what I've done today is, this is the lesson. I put 3 questions in a Google form just to practice. They're pretty quick. This is it for the unit, and so tomorrow will be review, and then we'll figure out a way to do a test. I'll probably just send it out following that. So try those 3 questions today. They should be pretty quick once you've gotten through these notes, and then we'll do some more practice with it tomorrow. All right. If we need an extra day to get ready for the test, let me know how you're feeling, if you want to just get it over with, or if you want some extra time. Either way is good with me. Okay, yeah, let me know if you have questions. Hopefully you're doing well.